Hello, statistics scholars. It's me again. I said that I would give a quick video on how to use the calculator. There are still some students who I recognized who don't feel as comfortable using the calculator as I need you to be, or that as you need to be, to move comfortably into the second half of the course. So I'm going to demonstrate how to use the calculator. I'm going to go step by step entering this data set. And as you remember, there are 30, the n size is 37. There are 37 years between 1981 and 2017. I'm going to enter that in the calculator, show you how to enter it, show you how to get the data that you need from the calculator, which is the n size, the mean of the sample, which on the calculator shows up as x bar, and get the standard deviation for all of the data that you need for this problem that you get 25 extra assignment points for. All right, so I'm going to go to the mat in a moment. You won't be able to see this data, but you will be able to see me enter the information on the calculator. So I'm going to just trust that you have the data set nearby, but really what you're watching is all the steps that I do to enter the data. Let's head over to the map. All right, so you have my calculator here. It's the same calculator that you have. And I'm going to enter the data, but I first want to sort of set you up to make sure you know kind of how to enter the data, how to clear the calculator, and what to do should you make a mistake. And so the first thing we're going to do, even though my calculator is cleared, we're going to hit second and reset to clear. It says, are you sure you want to reset? I'm going to say yes, and then hit the enter button down here. That enters or clears the memory so that the calculator is ready for entry. We're going to enter 37 pieces of data. So we're going to set the calculator up for data, second, and data. It's asking, do we want one variable or two variables? Until we get to correlations, which I think is 8, 9, 10, 11, 12, until we get to chapter 12, all of our data will be one variable. Correlations will be two, or we're correlating two variables. So we're going to say one, enter for one variable. And let's set the calculator up now for data. Second, sorry, just data. So it's ready for X1. So again, second and reset. Yes, second and data, one variable, and then data. It's ready for X1. So here's the data, 9.301, down one frequency and down again. So I'm ready for O2 or X2, 8.788, 9.173. See, I made a mistake. So I can just go back and type over there, 1824. 8.799, and I'm always moving past one frequency because I'm only entering one of that number. Nine point 141, 9.345, 9.076, and 9.378. That's 10. Great. That's the first group of 10. Ready for the next? 9.336, 8.974, 9.008, 9.175. Ooh, huh. Okay. So I'm at 13. That is 9.008. 9.175, 9.4, 9.168, 9.326, 9.660, 9.406, 9.332. That should be 20, yep. I'm ready for 21. 9.542, 9.695, 9.649, 9.451, 9.829, 9.662, 9.876, 9.581, 9.657, 9.828. That should be 30. Yep. Now I have 7 more. 9.650, 9.635, 9.753, 9.714, 9.662, and 10.160, and 10.0049. All right, so that's 37. That's the 38th. And now when I'm ready to see the results, I just press stat variable, and it starts to run the calculations. I can see that the n size is 37. That's what I expected. I go one to the right. I can see the uh, X bar, which is mean. I'm just sort of hesitating because that's not the number I expected. I expected 9.44, which is good. So let's go back and check. I'm going to go check really quickly. I should put on my glasses. I'm just going to press data and see 9.301, 8.788, 9.173, 8.824, 8.799, 8.985, 9.141, 9.345, 9.1, 9.345, 9.076, 9.378, okay. 9.336, 8.974, 9.008, 9.175, 9.484, 9.168, 9.326, 9.660, 9.406, 9.332. So far, so good. 9.542, 9.695, 9.649, 9.451, 9.829, 9.662, 9.876, 9.581, 9.657, 9.828. So far, so good. 9.650, 9.635, 9.753, 9.714, 9.662, 9.160, and 9.049. Okay. So we, in class, we perhaps round it up a little bit. So the n size is 37. The mean, the sample mean is 9.43. We were using 9.44. Not a big deal. We just rounded a little bit too much. That doesn't really change the results. And the standard deviation is 0.34, which we can round up to 0.35. All right, so let's run through the calculations. So let's write here, the mu is 8.79. That's what we think that's what we're testing the average land temperature historically. The mean that we just got was 9.434, or 9.43, right? There we go. The n size is 37, and the standard deviation is 0.35. All right, so let's work through the steps. 1, there is no difference in temperature. HA, there, mu, sorry, HO, mu equals 8.79. Got ahead of myself. Alternative hypothesis, there is a difference in temperature. Because we're interested in whether the temperature change is greater or less than, we're going to say mu is not equal to 8.79, which makes it a two-tailed test. Because you're looking for on one direction less than and the other section greater than. Right, so we need our critical value. We remember that the n is 37, which makes the degree of freedom is 36. Let's say the alpha we're doing is 0.05, and we're doing a two-tailed test. And you go to the T chart. We don't have 36, so we have to use 30. And we're looking for a two-tail. That means our critical value is plus and minus, because it's two-tail, 2.042. Draw the curve, 0, 1, 2, 3, -1, -2, -3. So the negative side, t equals negative 2.042, t equals 2.042 positive. Right at the rejection zone. And now we're ready to test our calculator test statistics. Let's figure out the standard error first. The formula is standard deviation divided by the square root of n. Standard deviation is 0.35 and n is 37. So 0.35 or 0.35, same thing, divided by the square root, that's second and the square button, 37. 0.00575. 0.0575. We're using two more digits because we're going to calculate it. So we can stop at 0.057, but let's use the whole thing. It's not a bad thing to do. Let's now calculate the t statistics, which is mean minus mu divided by the standard error. By the way, we know that if we continue to take samples of 37 from the same population, the mean 943 is not even going to move a whole point. So it's a pretty stable indicator or estimator of the true population mean. All right, so let's go ahead and do the calculation. 9.43 minus 8.79. Want to put parentheses around that because we want to get that difference first, and then divide that by the standard error, which is 0.0575. And if it's in the rejection zone, we're going to reject the null hypothesis. So left parentheses 9.43 divided by 8.79, right parentheses, see the parentheses right there, divided by 0.0575. We got 11.13, way out in the rejection zone, way off the page, right? So we're going to reject the null hypothesis that the temperature is not 8.79. This sample did not come from a population whose mean is 8.79. This mean is higher than 8.79. But let's see what the effect size is. The Cohen's d, mean minus mu, but this time divided by standard deviation, not standard error. So again, it's 9.43, which is the mean, 8.79, which is the mu, divided by the standard deviation, 0.35, which we got from our calculator. Anytime I press stat variable, I can, until I clear the data, I can still see what the standard deviation is and what the n size is and what the average or the x bar is. All right, so let's figure that out. Again, parentheses, 9.43 minus 8.79, close the parentheses, divided by 0.35. It's 1.82, which 1.828, which we can round out to 1.83, which is large. And now let's do our 95% confidence interval. 95% confidence interval equals mean plus and minus the critical value times the standard error. So the lower is 9.43. Since it's lower, it's minus the critical value, which is 2.042, times the standard error, which is 0.0575. Whatever that is, that's the lower number. The upper number is the exact same formula, except it's 9.43 plus 2.042, which is the critical value, times the standard error, which is 0.0575. But you can see this pattern right here. It's right here, right? So now we're going to put the parentheses around after we do 9.43. 9.43 minus, and then we're going to put parentheses because we're going to figure this out first. 2.042 times 0.0575, close parentheses. 9.312, so it's 9.31. And the upper, 9.43 plus parentheses, 2.042 times 0.0575, which is 9.547, which is 9.55. Okay, let me show you what this is. This, when we figure what this is, 2.042 times 0.0575. It's 0.117415, let's just say. All right. So what we're doing is saying 9.43 minus 0.117415. And we're saying 9.443 plus 0.117415. So if we just did 9.43 minus 0.117415, you see we get 9.31. And if we see 9.43 plus 0.117415, we get 955, right? So now we're going to make the decision based on the collected data from, I think it was from 1981. From 1981 to 2017. Now let's report the data. N equals 37. Mean equals 9.43. Standard deviation equals 0.35. Now let's talk about if we're rejecting or not rejecting. There is sufficient evidence to reject the null hypothesis. Great. A1 sample, t-test confirmed the effect was large. Then we report the t-test. We used 30, since we didn't have 36, equals 11.13. And since we rejected the null hypothesis, the probability, or the p, is less than 0.05, and the d equals 1.83, and the 95% confidence interval equals, we'll use that with brackets, 9.31, 9.55. So not only is the temperature that we got from the sample not is from a population whose average is not 8.79, it's higher than. So we reject the null hypothesis. But it's likely to be the population, the true population mean is between 9.31 and 9.55. And both of that whole range is higher than 8.79, which is why we reject the null hypothesis. All right, so I want to see 2 copies of that. You should have now some confidence. I want to see a picture of the standard deviation when you turn in the 2 assignments. And make sure you've done it 2 times. You don't have to do it 2 times in one sitting. It might be better to do 2 times in separate sittings so that you can allow it to seep into your brain. All right, hopefully that helped, and I am really looking forward to seeing how you deal with paired samples next week. All right, hopefully I'll see you on Saturday. If not, I will see you next Tuesday.